All right, so today I'm going to be going over Angular Ivy, what it is, its goals, new features that it brings to the table, and how you can make the switch to Ivy and take advantage of all these remarkable new things that the Ivy compiler has to offer. So just a little bit of background information. My name is Joel Parks. I work for GrapeCity on the Wijmo component library team. Wijmo, like I said, is a component library focused on data visualization and user input controls, which are available to be used in all of the major frameworks. So pure JavaScript, Vue, Angular, React. So now Ivy is Angular's newest compiler by the Angular team. It was initially released with Angular 8, but was made the default compiler for new Angular applications with the Angular 9 release. Ivy is replacing the Vue engine compiler, which had been Angular's default compiler since its release back in Angular 4. However, the Angular team has made it possible to still use the Vue engine in Angular 9. You'll just have to opt into using it over the Ivy compiler. Do note that anything after Angular 9, you won't be able to opt back into the Vue engine. Now, Ivy is a large step for Angular. It's a complete redesign of how the framework functions internally without changing the way that we as developers have to write our Angular applications. The redesign of Angular with Ivy serves two primary purposes, and that's to reach better build times through more incremental compilation and to reach better bundle sizes through improved tree shaking compatibility. The most important part of all of this is that as developers, we won't have to change the way that we write our applications. Ivy aims to be compatible with existing applications, and using it will be as easy as flicking a switch for most projects. Now, a big part of the push for this reduction of bundle sizes, though it improves loading performances across the board, is to help improve the user experience of users who are accessing the applications that we build through mobile devices, such as smartphones or tablets. As time has gone on, mobile device usage to access the internet has increased, with it accounting for 53% of all internet traffic within the US in 2019, and that number is only expected to keep climbing. Mobile devices, unfortunately, often suffer from bad or slow internet connections, making it harder for us to deliver the applications as fast as possible. We have solutions that can help us with this, such as using CDNs to serve files or progressive web apps to cache assets. The best opportunity that we as developers have is to reduce the bundle sizes that our applications produce. Now, along with these two main features, Ivy's also introduced a host of other improvements, along with the two mentioned above, such as improved build errors, faster testing, better debugging, improved CSS and style bindings, and improved internationalization. We're taking a look at each of these features in a little more depth throughout the presentation. We'll also take some time to go over any potential changes that developers may need to make, as well as building libraries compatible with both Vue engine and Ivy compilers, and consuming those libraries with your Ivy applications. The first improvement that we're going to take a look at is how Ivy helps us shrink our bundle sizes. Just as a quick refresher, bundling in JavaScript is an optimization technique that allows us to merge multiple JavaScript files together into fewer files, meaning that we can render our pages more quickly for our users. Now, what is tree shaking? Tree shaking is a term commonly used in the JavaScript context for dead code elimination. The idea is that all execution flows of a program can be represented as a tree of function calls, so that functions that are never called can be eliminated. One other thing that should be noted is that if you are using CommonJS to bundle your applications, Angular will now throw a warning when building your application using Ivy. The reason for this warning is that using CommonJS modules can result in larger bundle sizes when performing a production build. This is because CommonJS was designed to be used on server-side applications, meaning it was not properly optimized to run on client-side applications. If you're still using CommonJS, it's recommended that you switch to using ES modules to bundle your applications. To give you an example of what I mean, when importing functionality from another module, CommonJS allows you to pass a variable into the path, while ES modules requires it to be a string literal. If you take a look at this screenshot of code here, the first line is an import function for CommonJS modules, and the second is an import statement for ES modules. In the first one, in the require statement, you can see that we're passing along a path variable into the file path, whereas in the second one, it's just the entire path, the location. We're not passing in any variables there. CommonJS can take this dynamic approach because of how dependencies are loaded. When CommonJS needs to load modules, it's done at runtime. The modules are loaded, instantiated, and evaluated all at once. This is what allows you to do things like pass variables into file paths. Since this is done at runtime, it makes it harder for applications to perform tree shaking. ES modules, however, do not have the same problem. Because ES modules are more static, they're more statically analyzable. The loading, instantiating, and evaluation that takes place is broken up into 3 distinct phases that can be done separately instead of being required to perform them together, like with CommonJS. This allows us the ability for more efficient tree shaking. Now, how does Ivy allow tree shaking while the View engine does not, while making use of ES modules? It has to do with how Ivy updates the DOM versus how the View engine does. When the View engine first processes the application code, it makes a note of all associations between the HTML properties and the TypeScript properties. Then it goes about creating bindings, or a set of instructions for each HTML TypeScript property association. Since these bindings are component specific, it is easier to optimize them than some generic instructions. The resulting template data is then taken by the Angular interpreter and transformed into the DOM. So in the slide, you can see that there's a little diagram of the render pipeline for the View engine. So it'll take our template HTML that we write, convert that over into a set of template data, which then gets handed off to the Angular interpreter, which then converts it over to be used by the DOM. Whenever the bindings are created, Angular only deals with the bindings for change detection. When Angular is notified of a change, all bindings are reevaluated. This process is called dirty checking. After all bindings are reevaluated, the binding for which property is changed is then marked and updated. Finally, the template data is interpreted and transformed into the DOM with the latest bindings. With Ivy, instead of generating template data and passing it to an interpreter that decides on which operations to run, a set of template instructions is now generated directly. The template instructions are where the logic that instantiates components, creates DOM nodes, and runs change detection now lives. If you take a look at this Ivy pipeline render image, you can see that we've taken out the 2 sections, the template data section and the Angular interpreter section, and those have been combined into a single template instruction section, which uses the template HTML to create the DOM. The final thing to look at in regards to bundling is how much of a decrease in bundle size we see. The Angular team says that for small and large applications, we should be seeing a decrease in bundle size of roughly 20 to 30%, and that we should expect to see a slightly lower number for medium-sized applications. We've done some internal testing, and you can see our numbers here in the 2 images on this slide. Now, these tests show the bundle sizes using the View engine versus the Ivy compiler. The first column shows the widget controls that we have included in each project. So you can see in each one, we've included a different number of controls, different control combinations, etc. The second column is our bundle size output in kilobytes using the Ivy compiler. And the third is the bundle size output from the View engine, with the last column showing the bundle size percentage decrease between the 2 Angular compilers. You can see that from our tests, we're seeing over 30% decrease in cases of some of the smaller applications. As we get into medium-sized application, it hovers around 25%. When everything's said and done, we're seeing about a 30% decrease in overall bundle size, which is in line with the numbers that the Angular team were saying that we should expect to see. The second large change that we'll take a look at is the improvements that the Angular team has made in both application build times as well as improved build errors with the release of Ivy. When building your application, each build would force Angular to recompile everything inside of your module and would do so to check and see what had been changed in your code. It did this because the generated code of a component could be using the internal details of another component. Now, Each component references the directives and components it uses only by their public APIs. So if you modify an internal detail of a component or a directive, your application will know which other components the code uses the code that has been modified and only recompile those components. This can lead to massive benefits in build times for applications with a large number of components and directives. Now, instead of being required to recompile the entire application, you're only recompiling those components that need to be recompiled. We're going to take a look at a small example here to see what the changes look like in the compilers. So in this sample, we're going to be going over our mock component, car component, that takes an input value called car when the input is created. When the car component gets used inside of another component template, the code looks something like this. If you take a look at the app component.ts screenshot, and then the app component.html is how we are calling our car component. Now on the right side of the screen, you can see that the code that both the Vue engine and the Ivy compilers generated as a result of the input that our component requires. For Ivy, you can see the code here. Now, the Ivy code is only referencing the car component's public name. Contrast this to the code that is generated by the Vue engine compiler, which you can see. Here, the Vue engine generated code is only referencing the private field of car component. The difference that we're seeing here is because of Ivy's principle of locality. The principle of locality in Ivy means that in order to compile a component in Ivy, Angular only needs information about the component itself, except for the name and package name of its declarable dependencies. Most notably, Ivy doesn't need metadata of any declarable dependencies to compile a component. Now, this may just be a small sample, but this applies for large applications as well as small. All in all, the Angular team expects build times to improve roughly 40%. Now, the cool thing about these improvements the Angular team has made to Ivy is that Angular's AOT, or ahead-of-time builds, are noticeably faster. This means that the Angular team has been able to make AOT builds the default build in Ivy applications, both in developer mode as well as in production mode. Because of that, I'd like to touch quickly on AOT builds because the changes that allow for these kinds of builds in development mode and not just production mode have made other improvements to our applications that will be touched on later in the presentation. So I feel it's important to have at least a simple understanding of what AOT builds are. Now, AOT, or ahead of time compilation, converts your code from Angular to HTML and Angular HTML and TypeScript into efficient JavaScript code during the build phase before the browser downloads and runs your code. Compiling your application during the build process will provide faster rendering in the browser. Now, some reasons that you would want to use AOT include faster rendering. With AOT, the browser downloads a pre-compiled version of the application. The browser loads executable code so that it can render the application immediately without waiting to compile the app first. There are fewer asynchronous requests. The compiler inlines external HTML templates and CSS style sheets within the application JavaScript, eliminating separate AJAX requests for those source files. Smaller Angular framework download sizes. There's no need to download the Angular interpreter if the app is already compiled. The interpreter is roughly half the size of Angular itself, so omitting it dramatically reduces the application payload. Detect template errors earlier. The AOT builds detect and report template binding errors during the build step before users can see them. And finally, better security. AOT compiles the HTML templates and components into JavaScript files long before they're served to the client. With no templates to read and no risky client-side HTML or JavaScript evaluations, there are fewer opportunities for injection attacks. So along with these better build times, Ivy has also introduced better build errors that will show when you're building your application. So as you can see here, we've got two different build errors. Both of these, one in Ivy, one in the Vue engine, are for when you are calling a component that hasn't been imported into your module. So you can see the first one here, it just says that the app new component is not known. and then it's saying that if it is, add it to your module. If you look at the second one, it's showing the exact line of code that it's on and the exact file that you're seeing this in. So it clears up some of the readability here. The bullet points of the error message are the same. They let the developer know that the element that the user is trying to load may be a component, but it's not been included as a part of the module that's being built. So now we're going to take a look at some of the changes that Ivy has made to allow us to test our applications faster and more efficiently. With the release of Ivy, Angular now enables us to use ALT compilation in all phases, including the testing phase. This allows us to catch errors more quickly since we have fewer differences between the testing environment and the production environment. Along with this, the Angular team has also taken the opportunity to revamp Angular's implementation of the testbed class in Ivy to help improve some of its efficiency. In Ivy, testbed doesn't Previously, testbed would recompile all components between the running of each test or between each it statement, regardless of whether there were any changes to be made to components, for example, through overrides. In Ivy, testbed doesn't recompile components between tests unless a component has been manually overwritten, which allows it to avoid recompilation between a majority of developers' tests. With this change, the Ivy team has seen the framework's core acceptance test speeds improve roughly 40%. They stated that they expect users to see their own application test speeds to be around 40 to 50% faster than they previously were. The Angular CDK also introduces a testing subclass with version 9, which can be used to implement something called a component harness for test cases. Now, component harnesses hide implementation details of a component and exposes API, which can be used to retrieve important DOM attributes, such as ARIA attributes, interact with the component as users would without querying a component's DOM, and get harnesses of related components, such as child components or dialogues with menu triggers by the current component. Component harnesses can be used in unit tests, integration tests, and end-to-end tests. The Angular CDK comes with two harness environments out of the box. The first one is the testbed harness environment, which can be used for unit tests and integration tests. The second is the protractor harness environment, which is used for end-to-end tests driven by protractor. The testbed harness environment is first and foremost meant to be used with Jasmine and Karma, the de facto Angular unit testing stacks, which should work with other test runners and test frameworks as well. Now, we have a lot of tools at our disposal to debug web applications, from using simple logging statements in our code to browser development tools and web extensions. There are plenty of ways for us to tackle the issues of debugging our application. But the Angular team has given us a new tool with the release of Ivy, a global variable called ng. This new variable allows us to access corresponding Angular components. We can not only see the component properties and functions, we can also modify them in our browser's console and trigger change detection. To use the ng object, you'll need to have your application running in dev mode. With the ng object, you can ask Angular for instances of your components, directives, and more, manually call methods and update states, trigger change detection with apply changes when you want to see the results of your change detection. By doing this, you can avoid inserting unnecessary logging statements in your code because you can see the component state directly in your browser without any further tools. One of the errors that a lot of developers ran into that they hated to see during their Angular development was the expression changed after it has been checked error. The error output was pretty messy, which made it hard to debug the issue and find the root cause of it. And as you can see here on the screenshot, this is one of the errors from the view engine of the expression changed after it had been checked. Now, Ivy's updated the error messages a little bit. It looks pretty similar, but they've added some stuff to it here. So, for example, if you take a look at the app component template in the stack trace here, which was not in the previous stack trace, you can click directly on that, and it will take you from the stack trace right to the specific line in the generated code where the error is being thrown. If you'd like, you can also step into any of these framework instructions to walk through how the framework creates and updates your components. Now, the Ivy compiler and runtime provides improvements for handling styles, as well as the ability to use style variables inside of the HTML template itself. In previous versions of Angular, whichever style binding was evaluated last on the HTML element would be the one that would be the applied style. For example, take a look at the HTML here. So you can see that we're setting 3 different styles. The red color to our element. We're using the style attribute. We're using the style.color attribute. And then in the final one, we are using the style where we are passing in another variable to the color property. If my color and other color were both undefined in this case, then the static red would get ignored because it was overwritten by the styles that came later in the element. With the Ivy compiler, you can use a clear and concise order of precedence to determine which style will take effect when your code is compiled. With Ivy, the most specific style will always have the highest precedence. For example, binding the color of the element through the style.color property will override a conflicting binding to the style property. Another nice little change that was included is the ability to now use CSS variables inside of your HTML templates. You can see from this code snippet that we're setting our CSS variable inside of the div and then using that variable inside of the paragraph element down below. Like how TypeScript catches type errors in your code, Angular checks the expressions and bindings within your application templates and can report any type errors that it finds. With the move from the View engine to Ivy, the Angular team has made some improvements to allow for easier error detection with a full template type check setting, as well as adding a new setting, the strict template setting. Now, before we get into any new changes for type checking in Ivy, we'll do a quick review of template type checking in Angular 8. So the following component here will display a list of countries for us. As you can see here in the first screenshot, it's our component.typescript file. We have a list of countries here. We also have a title that is currently commented out. Inside of our HTML, you can see that we are trying to call the title, and we also are using the incorrect variable name for the country.code property. As you can see, the C is capitalized instead of lowercase. Now we're also setting the full template type check, which you can do inside of the tsconfig.json file. Now, once this is done, we'll run an ng build, and everything will compile successfully, and we'll even get some output here. But there will be some issues. So as you can see here, this list is the output of our application. As you can see that it's missing both the country codes as well as the title that we wanted to include above it. Now, we run into an issue when trying to build this application while using AOT, or ahead of time compilation, by running the ng build prod command. When we run this command, you'll see the following error, which you can see on screen here. When both AOT and the full template type check properties are set to, with AOT enabled and with full template type check property set to true, Angular can detect when we make references to a model that's missing from our component. Now, when the full template type check property is set to true and we're using AOT compilation, Angular is a lot more aggressive in its type checking within templates. Embedded views, such as those within ng-for and ng-if, are checked. Pipes are checked to make sure they have the correct return type. And local references to directives and pipes are checked to make sure they have the correct type, except for any generic parameters that they may have. Now we'll take a a look at how Ivy handles type checking when building a project. While using Ivy, we'll navigate back to the tsconfig.json file and make sure that full template type check is set to true. And now when we run the application using just ng-build, not ng-build prod, we'll see a similar error to the one that we had seen previously with the production build. As you can see here, it's saying the property title does not exist on type app component. But it's also giving us a little bit more information. It's telling us what file that error is occurring in, which is the app.component.html file. And it's also telling us that the title is what's causing the error. There's no title property inside of the TypeScript. It does not exist on type app component. Now, if you remember, Ivy uses AOT by default. So we're going to be seeing these errors without having to specify a production build. Because of the change in AOT being utilized in all forms of the build, developers will now be able to catch these template type checking errors sooner rather than later. If you go back into your app.component.ts file, we'll fix that misspelled code, and we'll also add back our title. We'll uncomment that out. And if we rerun it, we'll see the following output in Angular 9, or with Angular Ivy, sorry. You can see the title, countries, Angular Ivy, and that it includes both the codes as well as the country names. Now we'll take a quick look at the new setting added to allow for more type checking in Ivy, which is strict mode with the strict template setting. Strict mode is a superset of full mode and can be used by setting the strict template setting to true. Now in strict mode, Ivy adds checks that go beyond those in full mode, which is set with the full template mode, including verifying that components and directive bindings are assignable to their inputs, obeying TypeScript's strict null checks flags when validating the above, infers the correct type of components and directives, including generics, infers template context types where configured, for example, allowing correct type checking for ng-for loops, infers the correct type of event in components and directives, DOM and animation event bindings, and infers the correct type of local references to DOM elements based on the tag's name. Now, to enable strict mode, first you'll need to go back to the tsconfig.json file. Where we had the full template type checking, you want to replace that with the strict template setting and set that to true. And that will enable strict mode when you're building your applications. The Ivy compiler also makes improvements on internationalization and localizing your applications. Internationalization is the process of designing and preparing your app to be usable in different languages. Localization is the process of translating your internationalized app into specific languages for particular locales. To mark items that you want to add localizable messages to, you'll need to include the i18n attribute on these elements, like you can see here in this little hello world snippet. The Angular compiler will replace this text when compiling the template with different text if a set of translations was provided in the compiler configuration. These i18n tags are very powerful. They can be used in attributes as well as content, and they can be included in complex nested ICU expressions, as well as have metadata attached to them. However, there were a few issues that arose with the localization and internationalization in the view engine. The most significant concern was that translation had to happen during template compilation, which occurs right at the start of the build pipeline. The result of this is that the full build, compilation, bundling, minification, etc., had to happen for each locale that you wanted to support in your application. So if a single build took, say, for example, 3 minutes and the total build time was, or you wanted to support, say, 12 languages, that would be over 30 minutes to do all of those builds. Moreover, it was not possible to mark text in application code for translation, only text in component templates. This resulted in some weird workarounds where developers would create artificial components that existed solely to hold text that would later be used to be translated. And then finally, it was not possible to load translations at runtime, which meant that it wasn't possible for applications to be provided to an end user who might want to provide translations of their own. The Ivy compiler has been redesigned to generate a localized tagged string rather than doing the translations itself. This means that after the Angular compiler has completed its work, all the template text that's been marked with the I18N attributes have been converted to localized tagged strings, which then can be processed just like any other tagged string. Now, if you're using Angular 9 or a later version of Angular, your project will have an Ivy enabled by default. If you're currently working in Angular 8, you're currently using the View engine, which is enabled by default, unless you've decided to enable the Ivy compiler. Though it is recommended that you upgrade to a newer version of Angular if you intend to use Ivy. This will let you get the most up-to-date features and fixes that the Angular team has released for the compiler. If you're upgrading an already existing application to use Ivy, the Angular team has done their best to make it so that developers will have to do the minimal amount of work to get their application running with Ivy, but there still may be a few changes that developers will have to make. Now, if you're seeing errors while using Ivy in Angular 8, the first thing that you'll want to do is turn off Ivy. This can be done in the tsconfig.json file underneath the Angular compiler option setting, as you can see here. This is how you would enable Ivy in an Angular 8 application. If you want to disable Ivy, you'll just set enable Ivy to false. Now, like I said, if you're seeing errors while you're using Ivy, the first thing you'll want to do is turn Ivy off. Then you'll want to try running it again. If you're still seeing errors, then you know that this isn't Ivy related. If your application runs perfectly fine, then you'll know that you're probably running into some Ivy related issues. Now, some of these more common issues that you may see include the following. So by default, at content children queries will only search direct child nodes in the DOM hierarchy. Previously, they would search any nesting level in the DOM as long as another directive wasn't matched above it. All classes that use Angular DI must have an Angular decorator, like @directive or @injectable. Previously, undecorated classes were allowed in AOT mode only if injection flags were used. Unbound inputs for directives are now set upon creation of the view before change detection runs. And static attributes set directly in the HTML of a template will override any conflicting host attributes set by directives or components. Now, there's also a handful of less common changes, as you can see here, that developers may need to make. These ones are a lot rarer than the initial 4 that I had outlined, so we won't go over these in detail, but I will make the slideshow available afterwards, after the webinar is complete, so that if you would like to take a look at all of these, you can. Now we'll go over building and consuming libraries with Ivy. So with the change from the View engine compiler to the Ivy compiler, developers may wonder if they need to continue, if they will continue to be able to use libraries built in the View engine. Thankfully, the Angular team has created the Ivy compatibility compiler, or ngCC, to allow us to use libraries built in the View engine with the Ivy compiler. Now, the compatibility compiler parses the pre-compiled JavaScript code that gets produced by the View engine compiler. It then goes through and updates this code as though it had been compiled by the Ivy compiler. So if you're using libraries built within the View engine, but you're using Ivy, you will need to use the compatibility compiler. To do so, inside of your project's package.json file, you'll want to add a post-install npm script. So as you can see here, the post-install ngCC. This script will run on every installation of node modules, including those performed by ng-update, as well as ng-add. Now, the compatibility compiler works by scanning the node modules folder for packages that are in Angular package format, or APF, by checking the metadata.json files. The compatibility compiler will then produce Ivy-compatible versions for each of these packages. So if you are a library author or you are supporting any Angular libraries that people are using, the Angular team still recommends building your libraries with the Vue Engine compiler over the Ivy compiler. The reason for this is that Ivy-generated code isn't backwards compatible with the Vue Engine. So apps that are using the Vue Engine won't be able to make use of them. So if you release, say, an update that's built only in Ivy, if you have any users who are on Build Engine, they won't be able to make use of that newest build. Furthermore, the internal Ivy instructions are not yet stable, which can potentially break applications that are using different versions of Angular than the one used to build the library. So this means that if, say, you've built your library on a different version of Ivy than what your users are using, that may cause issues with your library. So what the Ivy team recommends is to just let the Angular CLI use the compatibility compiler to convert your Vue Engine generated code into Ivy compatible code. Currently, there's no need to rewrite your libraries inside of Angular Ivy. And that comes to the end of the webinar. That covers all of the major changes that the Angular team has been able to make with switching over from the Vue Engine compiler to the Ivy compiler. So I know that we've kind of covered a lot in this presentation, so I'd just like to do a quick rehash of the two biggest changes and reasons for switching over to the Ivy compiler. The first one being improved bundling. Ivy's changed how it handles rendering versus how the Vue Engine handles it. The Vue Engine created template data from template HTML, which it then used the Angular interpreter to translate that over to the DOM. Ivy has gotten rid of the interpreter and that template data, and now we just use template instructions to convert our template HTML over into our DOM. And the second is the improved build times. Now that the Angular team is making use of the principle of locality when building applications, we are seeing improved build times. The principle of locality means that in order to compile a component in Ivy, Angular only needs information about that component itself, except for the name and package name of its declarable dependencies. Ivy doesn't need any of the metadata of those declarable dependencies to compile a component, which has made AOT compilation much faster and the default compilation method for both dev and production mode. So as we've seen, there are some small changes that developers will need to make in that process of upgrading from the Vue Engine compiler to Ivy. But outside of any potential changes, the change done to Ivy is done in a way that we as developers won't need to change the base way that we write our applications, which gives us all the benefits of the changes that the Angular team has made on the back end. All right, that's it for my presentation here. I guess we can go over questions now.